Hello, everybody. In this video, we're going to take a look at the concept of average rate of change, and we're going to extend it with a look at the concept of the difference quotient, and which will kind of provide a little peek into calculus. All right, so we're going to begin by looking at average rate of change, right? So this is one of the key features of functions that we were looking at earlier. We looked at intervals, symmetry, parent function classes. Another feature of functions that we're going to emphasize is this idea called the average rate of change. All right, so what is the average rate of change? So if we're interested, the average rate of change answers the following question, right? If we say over a certain interval, how much is the function increasing or decreasing? Right? We looked at in class how to identify such an increasing or decreasing interval. Right? So we know how to identify such an interval, but the question then is how much, right? So we're interested in this quantitative question. Right? How much is the function increasing or decreasing? So we're going to use this by this idea of the average rate of change. But before going into the definition of the average rate of change, we have to define what's called the secant line. All right, so as with most things in math, it starts out, the average rate of change has a geometric foundation. And so we're going to build up the kind of the geometric intuition for the average rate of change, and then place the algebraic structure on top of it. All right, so we're going to begin with this notion of a secant line. So let's have a definition. Secant line. So let's say we have 2 points, x1, y1, and x2, y2. Let's let these 2 points let's let these 2 points lie on the graph of a function of f of x. So let x1, y1, and x2, y2 lie on the graph of a function f of x. The line that passes through these 2 points is called the secant line. So the line that passes So let's say we take any graph of a function f of x and we plot it, and we let x1, y1, and x2, y2 be 2 points on that graph. Right? We connect those 2 points with a line, and that line is called the secant line. Right? And so let's see an example of what a secant line looks like. So this is our definition of it. Let's visualize it here. Let's say we have a graph. We do our best to make it straight. We have a graph, or we have a plane, I should say. So we have a plane, and let's say we have the following graph on it. Let's say remember this is the graph of x squared. All right, so let's say that we have the graph of x squared on our line, on our plane. So now let's take 2 points. All right, so the idea is to construct a secant line plot 2 points so we're going to plot 2 points on the graph of f of x, and let's do that here. Let's say this is x1, and let's say this is x1, and this is x2. If we plot them, this corresponds to y1. Here's that point here. This corresponds to y2. We have a point here. All right, so now we have 2 points. The idea is now to connect these 2 points, with the line. So step number 2 is simply just to connect it. And so we connect these 2 points with a line. And we call this line this is called the secant line. And so now we have 2 points. We have x1, y1, x2, y2, and we plot those points on the graph of f of x equals x squared, draw a line connecting them, and that line is going to be called our secant line. And so when we ask the question, how much has our function increased or decreased over a certain interval, we're going to say what is the slope of the secant line that connects the 2 endpoints of that interval, right? So if we have our question, right, so our question again is how much has a function f of x increased or decreased over a given interval. So if we're asked this, we can answer that increases could be so the magnitude which is essentially the number. So the magnitude that function has increased or decreased over a given interval is equal to the slope of the secant line connecting, or say secant line line passing through the endpoints of that interval. So the question is, how much has a function f of x increased or decreased over a given interval? Our answer is that the magnitude of that function, the magnitude that a function has increased or decreased over a given interval is equal to the slope of the secant line passing through the endpoint of that interval. Right, so the slope of the secant line passing through the endpoints of that interval. So let's take a look at it geometrically. All right, and from the geometric view, we'll build up an algebraic equation. So again, let's say we have this coordinate plane here, and let's say that I have a graph that looks something like that. Make it a little. This is some function. All right, so let's say I have some function here, and the first thing I need to do is define my interval. So let's say that my interval is going to be x's between x1 and x2. And here I'm going to include x1 and x2 in my interval. All right, so my interval is x is between x1 and x2. So let's look at this interval here. So let's say I put x1 here, and I put x2 over here. So this is going to be my interval, right? And so I'm using this to construct a secant line. So the first thing I'm going to do is construct a secant line. And so let's say that we have this point here, this point here, and remember that we can think of y, since this is a function of x, we can think y is equal to f of x. So I'm going to call this line f of x1. All right, so we have x1, which gives us f of x1. And x2 gives us f of x2. All right, so we can start to see if we can start to see what we're doing here, right? So we're building up a secant line. So let's look at the secant line that passes through the two endpoints of our interval. And so I'm going to draw a line that connects these points. Let's try it again. All right. So we can see now that we're going to start to be able to build up a triangle. All right, let's think of the secant line as the hypotenuse of a triangle. And now what's left to us is to build the legs, right? So the secant line is going to be the hypotenuse of this right triangle. Do we have the rest of the information that we need to build up the legs, right? And we can certainly do this, right? Let's take the distance between x1 and x2, right? That's going to be the horizontal distance. So let's look. We have a right triangle. So our hypotenuse is given by the secant line. We're going to have a vertical leg and a horizontal leg. Let's look at the horizontal leg first, and we can see that the horizontal leg is the distance x2 minus x1. right? This distance here. This distance x2 minus x1 is the horizontal length of the triangle formed by our interval and the secant line, right? So we can just draw a straight line here. And we'll call this x2 minus x1. So this is our horizontal leg. Now the vertical leg of our triangle is given by the difference between over here. And we know that this is going to be f of x2 minus f of x1. Right, that's the distance between these 2 points. So I'm going to make a line here. I'm going to call this part f of x2 minus f of x1. All right, so now we have this right triangle made here by the secant line and our interval. And what we're interested in is the slope. So we're interested in the slope of the secant line. So let's make another picture here. Let's make another picture here and kind of zoom in on what we have. So we have this graph. So let's clean up this picture a little bit. And so I had x2 minus x1, and I had f of x2 minus f of x1, right? So if I want to know the slope of this line, which is the hypotenuse of this right triangle, I know that slope is equal to the rise over the run of a function. Right? The slope of a function we know is equal to the rise divided by the run. Right? So we already see here this f of x2 minus f of x1 is the vertical dimension of the interval, and we can say that this is the rise. Right? x2 minus x1 is the horizontal component of the interval, and we can say that this is the run. Right? So then our slope, which is m, right, we can see is going to be this is the rise over the run. Right? So if our rise was f of x2 minus f of x1, and our run is equal to x2 minus x1, all right, then we know that the slope of this line here is exactly that. F of x2 minus f of x1. So the slope of the secant line is f of x2 minus f of x1 divided by x2 over x1. And that tells us how much. That tells us how much the function has increased or decreased over a given interval. All right, so we can say definition so now we can have our algebraic definition and say that the average rate of change of a function f, average rate of change of a function f is going to be given by f of x minus 2 minus f of x1 over x2 minus x1. All right. So now we don't have to go through the steps of constructing a secant line, building a triangle, and then solving the slope. We just know that given some function and an interval range, x1 and x2, we can calculate the average rate of change. All right, so let's look at a couple examples. Let's look at a couple of examples. So let's look at the average rate of change. So let's look at f of x equals x to the fourth. All right? And we're looking for average rate of change of x. All right? Average rate of change. And here we're going to let the interval be, we're going to let the interval be so let's let this go from -1 to 0. All right, let's let this go from -1 to 0. All right, so step 1 is always to plug in our definition. F of x2 minus f of x1 over x2 minus x1. And now we just have to plug in. All right. From this, we know that x1 equals -1 and x2 equals 0. Right? So we're going to say f of -1 minus f of 0, which is wrong. x2 is 0, so we have f of 0 minus f of -1 divided by 0 minus -1. So what is f of 0? Our function is x to the fourth, so 0 to the fourth is going to be 0. Minus what is -1 to the fourth? So -1 times -1 times -1 times -1 is going to be 1. Times -1 is -1 times -1 again. All right. -1 times -1 times -1 times -1. All right. So 0 minus 1 divided by 0 minus -1 is the same thing as 0 plus 1. And so what is this? So this is going to be -1 over 1, which equals -1. So we can see that the average rate of change of x to the fourth from -1 to 0 was -1. Right? It went down. We can do this even if we have variables. Even if we have variables in the function, right? So let's look at the following example. Let's look at the example equals 1 minus 2 x to the third. And we'll say that that at the interval we have, and our interval is going to be equal to set x such that x is between a and 2a. So we're given the algebraic. So we understand that there's a geometric picture going on beneath this, right? That we can construct a triangle with the length, with lengths and heights, and do slopes and stuff. But right now, let's just look at the algebraic part of it and see if we can work from there. All right. First thing I need to do is identify my x1 and my x2. My x1 here is going to be a, and where I'm going is 2a. All right, now I'm ready to plug into the function. All right, the average rate of change of f is equal to f of x2 minus f of x1 over x2 minus x1. So here is going to be f of 2a. Right, x2 is 2a. Minus f of a over 2a minus a. All right, so here we're just plugging in. Step one is our definition. Now we're plugging in. And so now let's evaluate. Our step. So this is going to be definition of average rate of change. Step number 2 is plug in x1 and x2. Next thing we're going to do is evaluate f of x1 and f of x2. After we evaluate those, let's start with f of x2, right? So we have f of 2a. So we have 1 minus 2 times 2a to the third. Minus f of a is going to be 1 minus 2 a to the third. Right. This is over 2a minus a. We can simplify. We can simplify the denominator. 2a minus a is equal to a. Right. So now we still have quite a ways to go in simplifying the top. So let's give ourselves a little more room. Let's look at this 1 minus 2 times 2a to the third. So we have 1 minus 2. 2 to the third is going to be 8. And a to the third is 3. And then we have 2, a to the third is a to the third, so minus 2 a to the third. All that over a. And so we go back to this term, we still have some things. So we have 1 minus, distribute the 2, 1 minus 16a cubed minus 4 minus 2a cubed. All that over a. And so now we can take the parentheses out, and we have 1 minus 16a cubed minus 1 plus 2a cubed over a. You see that the 1's cancel out, and negative 16a cubed plus 2a cubed is negative 14. These cancel. Negative 14a cubed over a, which then simplifies to negative 14a squared. we said bring down what we're doing, average rate of change, like that. It'll be 14a squared. All right, so this is a more abstract example. All right, so we can do this still with algebraic expressions, right? So this is this notion about of average rate of change, and now we've seen it apply, right? Geometrically, what we're doing is the slope of a secant line. The essence of it, though, is how much does a function increase or decrease over that interval, right? So we saw a case here with x to the fourth, when we get a simple answer -1. We can also do it with a little bit more of an abstract answer and get an abstract problem, get a more abstract answer. Let's look at this notion of a difference quotient now, and take a little peek into the world of calculus. Right, so remember, let's bring back our graph of what was going on. Right, this was our f of x. And we had some x1 and some x2 from which we made points. All right, and we drew a secant line through these points. All right. And we calculated the slope of the secant line. All right. So essentially, this is what we're doing here, right? So, but let's redefine a few terms, right? So let's make let's just 1 second. Let x2 let's let x2 equal x1 plus h. All right. All right. So looking at this graph, right, I can see that I know that x2 is greater than x1. All right. Since I know that x2 is greater than x1, I can think of it as x1 plus some number, right? So since x2 is greater than x1, I know that it's just x1 plus some number, and so I can rewrite x2 as x2 equals x1 plus h. All right, so let's rewrite x2 as x1 plus h, and then rederive the slope of the secant line. All right, so again, we have a graph. Function on this graph, and I have a point x1, but now instead of having a point x2, what I have is a point x1 plus h. All right, so then coming over here, I have f of x1. Instead of f of x2, I have, let's try to make this a straight line. Instead of f of x2, I have f of x1 plus h. All right. Let's draw the secant line. So now I want to calculate the slope of the secant line. All right, look at the horizontal dimension. The horizontal dimension is x1 plus h minus x1, right? When I look at my horizontal, my vertical dimension, I have f of x1 plus h minus f of x1. Right. Our slope of the secant line is rise over run. So our slope then is going to equal f of x1 plus h minus f of x1 over x1 plus h minus x1, right? Since we have x1 plus h minus x1, those cancel out, and we have a slope f of x1 plus h minus f of x1 over h. All right, we call this the difference quotient. Right, so we've looked at this geometrically. All we've done is instead of calling it x2, we call it x1 plus h. And so instead of calling it an average rate of change, we're going to call this a difference quotient. Right. And so our definition of the difference quotient of f is going to be given as f of x plus h minus f of x. All right, we can drop the subscript 1 because there's only one x now. So we say f of x plus h minus f of x divided by h. All right, and we're going to divide that by h. One thing that we can see here is that h is not equal to 0. And so this is called the difference quotient. Right now, all we've done is a little bit of geometric algebra. Right? In calculus, we're not gonna, this you don't have to know for this class, but just, for fun. Right? For calculus, we're gonna ask the question, what if this h gets smaller and smaller and smaller? All right? All right, if we look here, the distance here is x1, is the difference between x1 and x1 plus h is h, right? But what if I make, and we get the secant line? All right, what if I make it, let's do it. Some secant line. All right, so we have one secant line here, but what if I keep making the distance smaller? All right. If I make this distance really, really small, I can get the slope of the curve at each point of the curve. Right? If I keep making the distance smaller, right? For any given x, right? How do I estimate the slope of a line of a curved line, right? At every point, right? The idea is that for each point, I make the distance h smaller and smaller and smaller, and then I can get the slope of a curve at any given point, right? So the idea here is if I make h smaller and smaller, then I can calculate slope of a function at any given point. All right, so up until now, we think of slope as something that requires 2 points. All right, we take 2 points and we get a rise and a run and divide that and we get the slope. But how do I get the slope at any given single point? All right, and the idea being we're going to switch from the slope of the secant line to a tangent line. And when h approaches 0, that secant line becomes a tangent line. All right, and so we can see like a brief example. The peak into calculus. Let's look at the example. Let's let f of x equal 2x squared plus 1. All right. What's the difference quotient? All right. The difference quotient of x. All right. So our definition for a difference quotient is f of x plus h minus f of x divided by h. All right. And so now let's plug in. All right. F of x plus h is going to be 2x plus h squared plus 1 minus 2x squared plus 1, and all that divided by h. So let's continue looking at this, right? So here on the side, we see that we have x plus h squared. So let's go ahead and FOIL that. I have x squared plus xh plus xh plus h squared. So I have x squared plus 2xh plus h squared. Well, looky there, we have our perfect squares formula again from the first lecture. All right, so factoring that, we can, or not factoring, but FOILing it, now we have 2 times x squared plus 2xh plus h squared plus 1 minus 2x squared plus 1, all that over h. All right, let's keep going. I can multiply, I can distribute this 2 out. Let's go ahead and do that. All right, 2x squared plus so I have 2x squared plus 4xh plus 2h squared plus 1 minus 2x squared plus 1. All right, now let's take everything out of the parentheses over h. Let's not forget that. So I got to distribute this negative, and that allows us to take everything out of parentheses. So I have 2x squared plus 4xh plus 2h squared plus 1 minus 2x squared minus 1. All that over h. All right, so now we're getting somewhere. Let's cancel some things out. So we have a 2x squared and a negative 2x squared, so that's gone. And I have a 1 and a negative 1, so that's gone. And I have an h on the bottom, so I can take this h out, and take the square out. All right. So that leaves us with, take all that stuff. But that leaves us with then 4x plus 2h. So 4x plus 2h is our difference quotient. Remember I said in calculus, if we want to get the slope of a line, slope of a function at a given point, we let h get smaller and smaller and smaller and smaller. All right, so just looking at this, if I asked you, if I say, what is slope So I said, what's the slope of 2x squared at any point in x? All right, then the slope is going to be the difference quotient when h goes to 0. So let's say that h goes really close to 0, like what's 2 times 0.000001? It's pretty much 0. And so I can say that it's going to be 4x. All right, so on your own, for fun, you can go into your computer and say b dx 2x squared, and it's going to equal 4x. All right, and this is calculus, but you already done it right here. All right, so by doing this difference quotient and thinking about what happens when h gets really small and close to 0, you're already doing calculus, right? So this goes above and beyond what we're going to test on in this class, but I do want you to understand that every one of you has it in you to do calculus. And I hope you see that it's a really fun subject, and that like we can extend what we know about functions from algebra quite a bit once we go into this world of calculus. But you're already there and you already know how to do it. So don't worry about it being hard or anything. I just wanted you guys to see that that you already have everything you need to know to do calculus. So so as a review, we looked at the average rate of change of a function geometrically and algebraically. Then we looked at the difference quotient and peeked into one concept of calculus, which is the derivative, and using the difference quotient. So thank you guys for watching, and I'll see you in class on Monday. Have a good day.